So today we will continue our discussion of symmetric functions. So recall that last time we proved several identities involving some sums. So the identities were the following. So for the product 1 over 1 minus xy ij, we gave several decompositions. First was called Cauchy identity, the sum over all lambda so it is given on page 2 on the top. That's formula 14. Then there was second identity that this is also equal to the sum p lambda of x, p lambda of y times factor z lambda inverse. This is formula number 13. We will need yet another formula which says that again this product is equal also to the sum again over all lambdas h lambda x1 times monomial symmetric function of lambda x1. So let's quickly prove this identity. It's not very hard. So recall that we know, so this is only y. Recall that we know that that this thing is very similar to generating function for the h functions. So this can be written, as we know, as product over all I or all j of sum k from 0 to infinity hk of x's times a to the power k. So this is just a function. This is just a formula for generating function of complete homogeneous functions. And now to get this formula, basically you just open the brackets in this product. You just multiply the factors. So you see that some of these h lambdas appear. Then you collect everything which comes with h lambda, and you see that you get exactly, sum over all. So here is ii, yi, and you see that you get exactly the formula for the monomial symmetric function. So this is simple proof. Okay, so these are three formulas that we will need. So our next aim. So recall that we were speaking all the time about lambda, which is a ring or algebra of symmetric polynomials in infinitely many variables. So now we want to introduce some additional structure on this lambda. Namely, we want to introduce some scalar product on lambda. So how do we do that? Well, to introduce some scalar product is the same as to say what is orthogonal to what. So we will say that the scalar product, which we will denote as brackets, this will be defined from the formula that we say that the basis h lambda is orthogonal to the basis m, mu, which means that scalar product of h lambda and m mu should be delta function of lambda and mu. So this is non-zero only if lambda is equal to mu, and then this is 1. So this is definition of our scalar product. Now, theorem that we need, or proposition. So we want to evaluate this scalar product on various functions, on p functions, on s functions, to understand how they behave under this scalar product. So we need the following proposition. So the conditions are equivalent. The following conditions are equivalent. Conditions are equivalent. So for what? For two bases, V lambda and U lambda in the ring of symmetric polynomials. So suppose that we have two bases in the ring of symmetric polynomials, V lambda and U lambda. And we can say first property is that they are orthogonal to each other. And U lambda times V mu is delta function of lambda and mu. This is first condition. And second condition is that sum of all lambdas, U lambda of x's times V lambda of y's is equal to 1 over 1 of product 1 minus xi ij. Okay, so why is this equivalent? So proof well, the proof is not very hard, so just write U lambda as sum A lambda nu times H nu. Since we know already that functions H are generators of our algebra, so we know that H lambda, their linear combinations span everything. That means that U lambda can be always decomposed as sum of these H functions. In the same way, write V mu as sum of B mu theta H theta, again sum over all Young diagrams, so again decompose these ones also. Then the first condition is equivalent, just substituting here and using the fact that these here M theta. And so scalar product is defined by saying that the bases H lambda and M mu are orthogonal. So this is the definition of scalar product. So decompose second basis into the basis of M functions. Then the first statement is just equivalent to the identity that sum A lambda nu B mu nu sum over nu is delta function of lambda and mu. But in the same way, the second identity just means that the sum lambda of x1 the lambda of I1 is equal to the sum of H lambda x1 lambda of I1. And again, substituting these formulas, we see that this identity is again equivalent to the same condition, which means that these two conditions are equivalent. Okay, so what it means for us? It means that we can evaluate scalar products of, say, Schur polynomials. Since this sum is delta function, then it means that S functions are orthogonal with respect to this scalar product. Also, since we know this sum, it means that scalar product of P functions, if this coefficient is again delta function times this coefficient z lambda. So Schur polynomials are form orthonormal bases, and these products of power sum form just orthogonal bases. Just a small remark. So we need a condition that two bases, these are indeed bases. So we need V lambda to be a basis and U lambda to be a basis. So we know already that H functions, M functions, P functions form bases. So this we proved at the first lecture. In principle, we don't know whether S functions form a basis, But to prove that, it is enough to note that from the very definition, we know that S function its leading term is monomial symmetric function, and then there is some sum C mu and mu over some smaller partition. So this just follows from the definition. If you just look at the definition as a ratio of of alternant and product, then you will see immediately that the leading term is exactly the same as in monomial symmetric function. Okay, so now we know this scalar product. So why do we need it? Why do we need this scalar product? Well, this scalar product lets us to define another very important object which will be intensively used in the next lecture of Alexei, which is a skew-Schur function. So if just Schur polynomial was parameterized by one Young diagram, skew-Schur polynomial is parameterized by two Young diagrams. So this is polynomial, so we'll denote it S lambda over mu. It's parameterized by two Young diagrams. So how to define it? To define it, we first need to do the following procedure. So first take two just ordinary Schur polynomials and multiply them. Okay, when you multiply two symmetric polynomials, you again get some symmetric polynomials. Since Schur polynomials form a basis, it means that you can again expand it as a sum of Schur polynomials. So this is sum C nu lambda mu S nu. So these coefficients of this expansion are known as Littlewood-Richardson coefficients. So as a side remark, it is known that these coefficients are non-negative, and there are two proofs of them for that. So first proof is that one can find just combinatorial expression for these coefficients. So these coefficients, they count certain objects, and since they count certain objects, they are non-negative. Another proof is of representation theoretic origin, so you can prove that these coefficients can be identified as coefficients of expansion of some representation into reducible components. But we won't say anything about the proof, and we won't need this statement that these coefficients are non-negative, but it is good to know that. Okay, now how to use these coefficients to define Schur polynomial, a skew-Schur polynomial. So this is the following. So you define this thing as sum of all nu's C lambda nu S nu. So what does it mean? Well, actually it means that you just want to define these polynomials so that they satisfy the following identity, that S lambda over mu product with S nu is the same as product of S lambda and S nu S mu. So basically what you see, that you see this product, here is lambda, here is nu and mu. And you want somehow to remove S mu here, somehow divide by it. You cannot just divide, in illegal operation, but you kind of divide so that you move mu here and define this function through this scalar product. And since Schur polynomials form orthogonal basis, defining scalar products with all its elements automatically define this function. Okay, so this is the definition of this skew-Schur polynomial. Now, why do we need them? Well, they have lots of very important properties. So the first property is that Cauchy identity, which I hope you still see here, can be extended to these skew polynomials. So we can prove what is called skew Cauchy identity. So this is the following statement. So in the simplified form, skew Cauchy identity tells that sum over all lambda. So if here we were summing just Schur polynomials, now we want to sum skew Schur polynomials. So first let's compute the following sum. So this sum still can be computed. And this is precisely S mu of I1 times product times 1 over product ij 1 minus xi ij. So note in particular that by the very definition, if this Young diagram mu is empty Young diagram, then skew Schur polynomial is the same as ordinary Schur polynomial. And you know, Schur polynomial parameterized by empty partition, this is just 1. And S lambda over mu, this is just S lambda. So it means that when mu is empty Young diagram, this identity just turns into usual identity that we have already proved. Okay, so how to prove this identity? Well, just compute the sum just by the definition. So let's write definition of Schur polynomials, skew Schur polynomials. So this will be sum over all lambda and nu, C lambda M nu, S nu of x's, S lambda of y's. So here we just substituted this definition given here to this formula. Now you can see that actually now we can first sum over lambdas in this identity. And here is, so C lambda mean M nu times S lambda. You can recognize in this exactly this sum, which means that this can be written as sum over nu S nu of x times S nu of y times S mu of I. So this is just by the definition basically. So what we see here now that this is sum over nu of this product times S mu, but we know that sum over nu just by usual Cauchy identity is precisely this product. So we have proved this. This is equal to that. So this Q Cauchy identity is just a corollary of just ordinary Cauchy identity. It can be even further extended. Namely, we can sum over two skew Young diagrams. So you sum over lambdas S lambda over mu S lambda over nu I1. And this again, and there is again expression for that. We will not prove it. So the proof is actually very similar to all the statements that we will prove today. So I hope that after today's lecture you will be able to prove it yourself. But the statement itself is written in the handout. So if you look at the formula number 21, so this is exactly formula for the evaluation of this sum. And that formula, if you look at it, you will see that precisely when nu is empty Young diagram, then this formula turns into this formula. And when both Young diagrams are empty, then you arrive at just Cauchy identity. OK, so this is Q Cauchy identity. Now, the next thing that we want to prove is to find some more explicit formula for these skew Schur polynomials as well as ordinary Schur polynomials. So for now, we don't know how are they related to H functions or E functions or to complete homogeneous functions, elementary symmetric functions. So now we want to somehow relate these two bases. So how to do this? So here is the theorem that first start from finitely many variables. So evaluated finitely many variables. Then this skew-sure function is equal to determinant of size n by n of the following matrix. So this is matrix composed of complete homogeneous symmetric functions. Is h lambda I minus mu j minus I plus j. This is our theorem. Yeah, so how to prove it? So to prove it, we will use some general principle. So we need this. So look at the formula at the very top. In principle, it explains us how to compute skew-sure polynomial in X's. More precisely, it tells that skew-sure polynomial in n variables is coefficient of polynomial S lambda in function S mu times this product. So now I want to just, by definition. So this product is symmetric function in Y's, so it can be decomposed into sure polynomials, and the coefficient is exactly our skew-sure polynomial. So now I want to say some general principle, how to find coefficient in decomposition in the sure polynomials. So suppose you have some function f. So there will be a principle, I suppose 3. So suppose you have some function f, and you want to find coefficient of the decomposition, alpha, lambda. So how to do it? Well, we should just recall the definition of sure polynomial, that this is alternant. So this is the sum over lambdas, a lambda times alternant of x1 to the power lambda 1 plus n minus 1 times xn to the lambda n, and everything divided xi minus xj. Now note that all the monomials appearing in this sum are distinct. So if you write alternant as a sum again, so you will get only distinct monomials, which means that the coefficient a lambda is the same as coefficient in the function fx1 xn times product xy minus xj, coefficient of the monomial x1 to the lambda 1 plus n minus 1 xn to the lambda n. So coefficient of this monomial in this function is the same as coefficient a lambda. Okay, so how to use it in our case? Well, then just multiply and see what's happening. So let's do it. So we need to extract coefficient of monomial I1 to the lambda 1 plus n minus 1, In to the lambda n, in following thing. So we take first alternant I1 to the mu1 plus n minus 1 n to the mu n. So this is a factor coming from Schur polynomial. And then this product we will again expand using the generating function for h functions. This product over j sum over k hk of x1 xn times ij to the power k. Okay, now this coefficient, just when you open the brackets, multiply, you see that this is equal to the sum of all sigmas. It's 1 to the sigma. So the sum comes from the alternant, basically, of h lambda plus delta, whereby lambda plus delta I again mean this operation of adding to lambda 1 n minus 1 to lambda 2 n minus 2 and so on, plus sigma plus sigma of mu plus delta. Here I simply mean, so again you add to mu this coefficient, you get this thing, then you somehow permute the coordinates. That's what you should do when you compute an alternant, and that's all. So this is just from this formula, and then you immediately recognize that this sum is nothing else but this determinant. So this formula is proved. So again, it is written in the handout as the formula number 19. You can see that in particular we can use it when mu is empty Young diagram to compute the Schur polynomial, and in this case this formula is known as Jacobi-Trudi identity. Okay, now we need next identity, which is the following. So skew-Schur polynomial. First we know that, again, since we know this identity for finitely many variables, we can again send the number of variables to infinity and say that we have the same identity for the infinitely many variables. The only question is, what is the size of determinant? So it seems like we need an infinite determinant. But it's easy to see that actually it doesn't matter. So you can take determinant of any size which is greater than the number of rows in your Young diagram, and you will get the same formula. Just as a small remark, maybe you're wondering what is happening here when the index is negative. So we assume always that hk is 0 if k is less than 0. Now there is a second formula of this kind. It's called usually dual formula. This is the statement that the Schur polynomial is also determinant of E prime minus mu j prime minus I plus j. So in the same way as in previous lecture, these primes, they mean that we want to view our Young diagram of partition lambda as a picture. And then coordinates lambda prime are just column lengths in this picture, while lambdas are row lengths in this picture. So how to prove this formula? Well, this formula follows from the first formula. Proof. Now that we know the identity, which is written in the handout as identity number 5, which relates E functions and H functions. Now, this identity can be also rewritten that if you consider the matrix H, which is matrix H j minus I, and matrix E, which is minus 1 to the g minus I times E I minus j, then the identity just states that the product of these two matrices is identity matrix. So H times E is identity matrix. Also know that again, we assume here that HK is 0 as soon as K is less than 0, which means that this is actually upper triangular matrix with 1s on the diagonal, which means that its determinant is 1, as well as determinant of this matrix. Now, there's a general fact from linear algebra that if you have two such matrices, then any minor of H is equal up to sign to the complementary minor in E transpose. So perhaps everybody should know this statement for the case when we speak about minors of size 1. It says that minor of size 1 is just matrix element, and it is known that there is a formula for inverting matrix that the matrix element of the inverse matrix is the same as minors of the size n-1 in the matrix itself. So this is just some extension of this fact, which is again proved by some linear algebra. We won't prove it. And now you can see that actually this is exactly the statement. So as soon as we have this determinant, I'm claiming that this is exactly this complementary minor. So how to see that? We should somehow understand that the set lambda I minus I is somehow complementary to lambda pi I minus I. So to see that, just look at your Young diagram and see that we can identify this lambda I minus I. So look at the boundary of your Young diagram. You can identify lambda I minus I with these points on the vertical segments of the boundary. In the same way, you can identify these points with points on the horizontal segments of the boundary. And then you clearly see that these sets are disjoint. Because there is a question how we number these. So maybe there is some shift involved. But notice that in this determinant, shift doesn't matter. If we shift all the coordinates, then determinant does not change. OK, so this proves that this determinant is equal to this determinant. Are there any questions for now? OK. Now there are two important corollaries. First is that corollary 1 is that S lambda over mu is 0 unless mu is subset of lambda, which means that mu I, that each coordinate lambda I is greater than mu I, or equivalently that each coordinate lambda 1 prime greater or equal than mu I prime. So in Young diagrams means just one Young diagram is a subset of another Young diagram. So how to see that? Well, just look at this determinant and notice that if this condition is not satisfied, then this matrix, just from this condition, will have a huge block of zeros, and its determinant automatically will be equal to 0. So this is corollary 1. Now corollary 2 is the following, that if we evaluate now in only one variable, so all variables except for one are zeros, and we evaluate at one variable, then this is 0 unless we have the following inequalities. So what these inequalities mean? So it says the following. So you have your Young diagram lambda. And now you have some mu. Okay, suppose this is mu. Now you have lambda, which is bigger, but not much bigger. So you need that in each column, you add at most one box. So, so lambda here is this Young diagram with row length 4 and 2, and mu is this Young diagram with row lengths 5 and 4. So the condition tells that in each column we add at most one box. And this will be denoted that mu, okay now. So we would, so this is, the big one is lambda. This is some number. So we can evaluate in a single variable. So we set all the variables except for one to 0 and one variable to theta, and we want to evaluate it. We say that this is 0 unless these properties are satisfied. We will write it that mu precedes lambda. It's also, sometimes people say that these Young diagrams differ by horizontal strip. So this figure, which has at most one box in each column, is usually called horizontal strip. And finally, if this is satisfied, then otherwise this is equal to the theta to the power number of boxes in lambda minus number of boxes in mu. Okay, so how to prove this? To prove this, know that when we evaluate in one variable, then we have that elementary symmetric polynomial 0 in one variable is 1. Elementary symmetric polynomial first one in theta is theta, and all greater ones are 0. So this is just by the definition. Then look at this formula and notice that again, if these conditions are not satisfied, then this matrix will have a block of zeros and it will evaluate to 0. If these conditions are satisfied, then this determinant is just a product of matrix element. Each of them is theta, and so we arrive at this formula. Okay. So now let us continue. So more generally now we want to, so here we found expression for the polynomial evaluated in one variable. We want to find the expression for the polynomial evaluated in any finite number of variables. So how do we do that? So this is the following theorem. So first part, S lambda of x1, xn, and okay, it's better to write it this way. So suppose that we have two sets of variables, x's and y's, and we substitute all of them. Since we have infinitely many variables, we can always say that half of them is called x's, half of them is called y's. Then we extend it as symmetric polynomial separately in one set of variable and another set of variable. And then we have the following formula. Okay, so how to prove it? Well, just sum of all lambda and mu, S lambda over mu of x, S lambda of z. So x it will be some set of variables, z will be second set of variables, and y will be third set of variables. This is equal just by this Q-Cauchy identity that we proved recently to product over ij 1 minus xi zj times sum. So we summed over lambdas first. So this sum follows from Q-Cauchy identity times sum over mu, mu of z, mu of y. Okay, now this sum again can be evaluated by skew Cauchy identity, but just by usual Cauchy identity. And we get that this is product ij y minus xi zj times product over ij 1 minus 1 minus I zj. Okay, but this can be written as a single product. And then as a single product, we can apply Cauchy identity to this again and get that this is in the same way that this sum over lambdas s lambda of x1 da 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 I1 da 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 times s lambda of z variables. So this is just Cauchy identity. Now comparing the coefficient of s lambda of z here and here, we arrive at this identity. And this identity can be further generalized to the skew polynomials, saying that s lambda over mu is equal to sum over all nu s lambda over nu in x's s nu over mu in y's. So this generalization is proved pretty much in the same way. So let's stay with the first identity. Okay, now this identity allows us to define to give very important formula. Namely, let's suppose that we have evaluate s lambda of x1, xn, and some parameter y. So when now we use it for single variable. So by the formula, we should compute this sum over mu s lambda over mu y s mu of x. But we know that this Q-short polynomial evaluated in single variable is this thing. It means that this is just a sum over all mu preceding lambdas, where this is this condition, this horizontal strip, y to the minus mu So this formula is usually called the branching rule for the Schur polynomials. So it gives expansion of Schur polynomials in n plus 1 variables into Schur polynomials in n variables. It is also given in the handout as formula number 10 on the first page. Now what is more important, we can iterate this formula. So we now can again expand n variable in n variables into polynomials in n minus 1 variables and so on. In the end, if we do this process, we arrive at the following formula, which is known as combinatorial formula for Schur polynomials. So to write this formula, we need some notations. So suppose that you have your Young diagram lambda. We will introduce what is called semi-standard Young tableau of shape lambda. This is a filling of this Young diagram with numbers. We have some parameter n. We fill this Young diagram with numbers 1 to n in such a way that along the rows the numbers are weakly increasing, which means that they can be the same, like 1, 1, maybe 2, 2, 3. In the same way, along the columns, numbers should be strictly increasing. So something like maybe 2, 2, 3. So here we should have strict inequality. Here we should have weak inequality. So any such filling is called semi-standard Young tableau. And we have a parameter n, which is the maximal number. Not maximal number, so this is, no, all the numbers are not greater than this parameter. And then you can see, just iterating this formula, that you arrive at the following statement, that s lambda of x1, xn is equal to the sum of all semi-standard Young tableau. You can see that if you look at, say, 3s in this Young diagram, then they follow exactly horizontal strip. So there is at most one in each horizontal column, in each vertical column. If you look at 2's, they again form horizontal strip. And once again, so this semi-standard Young tableau, this is just a way to write these conditions. And then you arrive at the formula that this is sum over Young tableau, as we call it, x to the t, which means simply that this is sum over this semi-standard Young tableau, x1 to the number of ones, x2 to the number of 2's, and so on, xn to the number of n's. Okay, so this is the formula, which is known as combinatorial formula for Schur polynomials. It's formula number 11. In principle, there is an approach to Schur polynomials which uses this formula as just a definition. This is very explicit sum of all these combinatorial objects. However, notice that if you use it as a definition of Schur polynomial, that, for example, the fact that Schur polynomial is symmetric is already non-trivial, because from here, the symmetry in variables excites. I don't know, you can prove it, but it needs something. Okay. And I also want to remark that there is a similar formula for skew-Young diagrams. Basically, it will be again sum over all tableau x to the t. Only now you will have to look at the skew tableau. What is skew tableau? Well, basically, if lambda is this Young diagram, and then mu is, I don't know, these two boxes, then you just fill with numbers set theoretical difference of lambda and mu. And this is your skew tableau. So but the formula after that remains the same. And the proof also is exactly the same. Okay, so we end up with Schur polynomials for now. And we will come back to specializations, which were discussed at the end of the previous tutorial. So recall that specialization is just a homomorphism from the ring of to the complex numbers, from symmetric polynomials to complex numbers, that we usually define that the function f is mapped to f of rho. This is just a notation. Now we will define Schur positive specializations. Which is a specialization rho such that S lambda of rho is at least 0 for any lambda. So this is such a specialization which is non-negative. You may ask, why are we interested in such specialization? The answer is simple, because we want to study some probability. If we want to interpret these numbers as some probabilities, they need to be non-negative. So that's why we're interested in this non-negative number, only in non-negative numbers. Okay, you can see as a corollary, as I told you, that Littlewood coefficients are non-negative. It means that this actually will imply that even for any lambda and mu, skew Schur polynomial, this image of skew Schur polynomial under this specialization is again non-negative. This is just fact which follows from the non-negative of the coefficients. Okay, now it turns out that there is a complete classification of all Schur positive specializations. It turns out that any such specialization are parameterized by two sequences of numbers. We have sequence alpha. Alpha 1 is greater than alpha 2, greater than 0. So there are two decreasing sequences of numbers and betas. Beta 1, beta 2. An additional number gamma, which is also non-negative. The only condition that we have is that sum of all alphas plus all betas should be less than infinity. And then given that, we introduce the formula for general specialization. So we have specialization rho, alpha, beta, gamma. So let's study value of this specialization on complete homogeneous functions. So we study the sum k of rho z to the k. So this is the value of specialization on complete homogeneous functions. So since they are generators of the algebra, it's enough to put these values. And the formula is the following. So this is e to the gamma z, product of all I, 1 plus beta e z, 1 minus alpha I z. Now you can see why we need this condition. The sum is less than infinity. It just guarantees that this series is converging. Otherwise, it won't be convergent. Another formula, we can also specify the values on other generators, say on the p functions. So first power sum of rho will be just sum of all alphas, betas, and plus gamma. More general pk with k greater than 1 will be given by more delicate formula. Sum alpha I to the k plus minus 1 to the power k minus 1, sum beta I to the k. Okay, so these formulas are given again in your handout, somewhere on the second page. And this theorem, it turns out that this theorem has lots of connections with different areas of mathematics. So it is equivalent to some representation theoretic fact. It is proved maybe almost 50 years ago already by Thoma, such a German mathematician. After that, there were different proofs and extensions by Vershik and Kerev and Okunkov and Alshansky. So this theorem has lots of history. We will just give you, to the end, I will just give you two connections to show that this is indeed somehow related to representation theory. So first note that if we have only finitely many alphas here and no parameters gamma and beta, all of them are zeros, then this formula just tells us that we are just substituting the variables. As you can think about, just put instead of variable x, variable alpha. Because then this formula just turns, if this is not present and this is not present, this just turns into the Cauchy, to the generating function for the h functions. So, but clearly this specialization is positive because we know the combinatorial formula, which is written still here. And you can see that if all x's are non-negative, then clearly the values of h-sure polynomial is non-negative. So this is what we expected. In particular, if you consider the following case, you take specialization rho with n parameters alphas equal to 1 and all betas equal to 0 and gamma equal to 0, then then we, from the combinatorial formula, we see that S lambda of this number of ones is the same as number of semi-standard Young tableaus of shape lambda filled with numbers 1n. But then it turns out that this number has representation theoretic interpretation, which is that this is dimension of the irreducible representation of unitary group of size n, which is just group of all n times n unitary matrices. So it is known that representations of such groups are some of them are just given by these Young diagrams. So reducible representations are kind of parameterized by these Young diagrams. And then it turns out that this combinatorial number, which is this evaluation, is just exactly the dimension of the reducible representation parameterized by lambda. So this is first fact. Now the second fact is, turns out that if you consider specialization in gamma, then it's again related to representation theory. So let me state it. So if you now consider rho such that gamma is equal to 1 and all alphas and betas are 0, then lambda of rho is some number. Well, notice what it says is that P1 is mapped to 1, all other PKs are mapped to 0, which means that to evaluate the value of Schur polynomial, you should decompose Schur polynomial into the sum of p functions, then substitute 1 instead of p1 and 0 instead of everything else, which means that this evaluation is the same as scalar product of S lambda and p1, the number of boxes in lambda. This number has again some combinatorial interpretation, which is the following. Again, you have your Young diagram lambda. Now we will speak about standard Young tableau. What does it mean? It means that now this Young diagram has n boxes, and we are filling with numbers 1 to n. So all the numbers will be distinct. And again, we will demand that they're increasing in rows and columns. So something like that. 4, 5, 6. So this thing can be shown to be equal to the number of standard Young tableaus of shape lambda, which is again known to be equal to other dimension of reducible representation. This is dimension of the irreducible representation now of symmetric groups, so of all permutations of n letters. And it is known that representations of this group are again parameterized by by Young diagrams, and this is exactly the dimension of the representation. Okay, to end up, maybe we can prove actually this formula that this is equal to number of standard Young tableau of shape lambda. It is not hard to prove, because let us expand S lambda as sum over all mu, C of lambda mu, and mu. So this expansion of Schur polynomial into monomial symmetric functions. You can see that this extension is actually known from the combinatorial formula, because we know how to extend into monomials, but monomial symmetric functions, they're actually pretty much monomials. But then, since we know that this p1 is the same as h1 to the power lambda, and we know that h functions and m functions are orthogonal, it means that this scalar product is equal to the C lambda and Young diagram and one column Young diagram, 1, 1, 1. Which means, if you look at the combinatorial formula, that you are summing over semi-standard Young tableau such that all the entries are distinct. But semi-standard Young tableau with all distinct entries is nothing else than standard Young tableau. Which means that, from the combinatorial formula, you arrive to this formula. Okay, I think I will stop here, and I want to remark that next lecture will be absolutely different. We won't speak about symmetric polynomials anymore. So on the next lecture, so tomorrow, Alexei will introduce some stochastic dynamics related to Schur polynomials, and I will show you some pictures, movies, and so on. So explaining how this turns into real probabilistic models, and give you some understanding of what's happening in some graphical images. So thank you.